All right, well, good deal. I think we can get started. It's 1:02. We may still have a few people signing on late, but that's okay. So I just want to say welcome. Thanks for joining, everyone. I see quite a few familiar names. For those I have not met, good to have you on board. My goal today is to cover technical and economical aspects for biogas projects within industrial wastewater here in North America. Um, Industrial wastewater includes a very wide array of different projects, ranging from the biofuels industry to meat and agriculture, confectionaries, bakeries, dairies, brewing, distillation, and the list goes on and on. Our team has many, many decades of experience with anaerobic digesters, not just within North America, but globally. So most of what we'll discuss today will actually be our own experience. Just a quick introduction about myself. I've been in the industry for a little over 15 years. Within that time frame, I've primarily focused on industrial wastewaters, with some municipal work kind of spliced in between there. First and foremost, I would consider myself more of a process engineer. That's just kind of how I was raised, much more on the technical level, but I do manage business development for Fluence within North America, specific to industrial wastewaters. So basically what we'll look at today are the recent tax incentives for biogas utilization projects. There's currently a lot of interest, a lot of, I would say, conceptions or misconceptions on the markets, as the tax incentives were recently updated this past August. So it's really only been less than a year that these tax incentives have really come front and center and have been updated for the public. So that's what we'll try to target today. If you have any questions along the way, I think you can use the chat feature. Just jot down a question, a note, text it over. I'll try to get to the questions as we go through, and if I don't, we'll definitely have 10 or 15 minutes of free time at the end where I can go through and catch up on the chats and answer any questions there. Otherwise, if you have to jump off for any reason, my email address and my phone number is right here on this first slide. So please feel free to send me an email, shoot me a text, give me a call, and we can speak in more detail. So just to give you an idea of agenda for today, the bulk of the presentation should take about 35 or 40 minutes. We'll cover technical and economical areas related to biogas projects, anaerobic digestion, and the tax incentives. So my focus is to spend more time on the tax incentives so that you guys clearly understand how the new Inflation Reduction Act is playing into these digester projects and development projects. And when we talk about these projects and waste to energy projects, it can be site specific. It can be, specifically for your site, where you have a definitive need, and anaerobic is a good fit, or there may be some developers interested in doing more like cogeneration facilities. That is also an option. Just to be clear, the tax incentives cover whether you're a private industry or you're going after larger regional cogen facilities as well. So I'm assuming that most people on here have some basic understanding of anaerobic digestion, but I'll give a quick 5-10 minute overview of waste to energy in general so that everyone kind of has a basis for moving forward in the presentation. And again, if you have any questions, feel free to use that chat feature. At the end of the presentation, we'll circle back and try to hit any topics or questions raised throughout this. So quick background on Fluence. Fluence is a multinational engineering and manufacturing organization. Here we show our offices, engineering offices, sales offices, and production locations. Our headquarters is based in Minnesota, just in Minneapolis. Right now, we're doing business in about 80 different countries, so we're able to support every major continent, more or less. Essentially, anything related to water and wastewater, Fluence is probably in it. We have multiple divisions focused on everything from potable water to desalination, decentralized plants, industrial process water, wastewater, municipal water and wastewater, and the list goes on and on. For today's presentation, I'm specifically focusing on the industrial wastewater operations. I think the majority of you who signed up are more on the industrial side, so that's what we'll focus on today. Just for your, I guess, knowledge, our industrial operations, our industrial team is jointly managed between the U.S. and our Italian wastewater operation group. So myself, I manage the business development here in North America. So any local projects here, I will definitely be, your go-to if there's any technical questions or anything like that. Please feel free to reach out to me. We have a large team, roughly 4 people, supporting the U.S. industrial operations. So I think the best place to start is waste to energy in general, just going over the fundamentals of what we mean when we talk about waste to energy, and how that kind of rolls into the overall return on investment ROI picture for these projects. There's a lot of different treatment categories that are associated with biogas projects. A lot of times we'll have not only the anaerobic system, but we'll have a separate or tag along wastewater system or a reuse system, or potable water system in some cases that kind of are bundled with these waste to energy projects. So I just wanted to point out that in some cases, it's possible to roll or incorporate other aspects of water wastewater treatment into biogas projects under this tax incentive umbrella, if you will. Typically, when we're doing waste to energy projects, the minimum tax credit that we see is about 30%. And I'll get into the details on how this is broken down later in the presentation, but just right up front, so everyone has, a basis for moving forward. Anytime we put a capital expense on the table, or a cost of a project on the table, roughly 30% of that generally is qualified or approved for a federal tax credit. So hypothetically, if the cost of your waste to energy project is $1 million, most of the time 300,000 of that is available as a tax credit. So the realized value is closer to $700,000. Again, just as an example. The maximum, as written into the Inflation Reduction Act, is 50%. I will say in practical operation, the highest project that I've personally been involved with had about a 45% tax credit on that project. Not to say that 50 is not possible. There's just some additional kind of bonus areas that you really have to be aware of to really maximize and reach that full 50% value. So let's talk a little bit about waste to energy and what we mean by waste. So when we talk about waste, we're typically referring to either wastewater or byproducts of manufacturing, industrial manufacturing. That could be, food, beverage industry, so meat, chocolates, breads, veggies, fruits, as well as CIP processes, or even just the primary wastewater discharge from a manufacturing facility. To consider a waste to energy process, the waste obviously needs to be organic in nature, so it needs to have a readily biodegradable BOD value. We normally like to see a minimum BOD value of 2,000 milligrams per liter in terms of concentration based. Below that, and the economics kind of stretch out a bit. So in general, higher BOD values and low flow situations have the most favorable ROIs in terms of how quickly the project pays for itself. The basics of waste to energy are pretty simple. You basically take an organic waste, put it into a tank without oxygen, And under the absence of oxygen, the bacteria that accumulate or that acclimate take the hydrocarbons, take carbon, take hydrogens, put it together, make CH4, basically make biomethane. Um, just for, so everyone can kind of compare, biomethane versus other forms. Biomethane being CH4, propane, for example, is C3H8. Then you have compressed natural gas, liquid natural gas. They all have different, kind of a different chemical structure, but they are all somewhat derived from the same base natural gas product. The physical application is a bit more involved. So here, what I want to demonstrate on this page is understanding feed source is probably the most critical element for a proper waste to energy design or anaerobic design. So we typically like to break down, uh, you can call it waste, you can call it feedstock, you can call it wastewater, however you want to define it. They're all kind of the same here, and I'll use them interchangeably a lot. There's five main categories that we typically break it into: lipids, oils, fats, greases, things like that, animal proteins, then you have vegetable proteins, then you get into complex carbohydrates and simple carbohydrates. Um, in terms of the weight of organic uh, nature versus the weight of the waste product or feed product that you're putting in, those five categories all carry different energy values. And therefore they all have different degradation time. So understanding the feed source uh, directly impacts the ROI because it directly impacts the type of digester that we determine is going to be the best fit. It directly impacts the size of the digester. It directly impacts how much gas output there's going to be or how much we can anticipate. And it directly impacts the performance and the stability of the process. So understanding the composition and degradation time are critical as a first step. So yeah, understanding how all these feeds can be applied or if they can be combined in some cases really plays a big part on return on investment. And when we talk about return on investment, basically what I'm saying is how quickly does the system pay for itself? And methods of paying for itself can be either reduction in sludge or energy production or gas production that can be used for offsetting your current natural gas needs, taking the biogas all the way to renewable natural gas where you can put it into a pipeline. There are a lot of different ways that this can be repurposed. As long as the biogas is being repurposed and not flared, it will qualify for a tax credit. So basically understanding these feedstocks, we can determine where's the value. Is it in reprocessing byproduct or your waste product? Do you have more value using it as an animal feed byproduct? Is there more value using it for biogas utilization? So all this, how does it drive the capital expense for a waste to energy project? In addition to the previous table here, we've kind of broken down the theoretical values of different feed sources or byproducts or waste products, however you want to define it. So in terms of the mass load of organics versus, the mass load of these waste products that you're putting into a digester, it shows how much potential methane can be produced. So we can take this methane and we can convert it into electricity. We can convert it into thermal energy. The most simple form of repurposing biogas, and I apologize, I use biogas and methane interchangeably sometimes. Technically, biogas consists of a combination of methane, water vapor, and CO2. So the methane content is typically less than what the actual biogas content is, obviously. So um, the simplest way to repurpose and qualify for tax credits is to basically take this methane and use it within an existing boiler. So That boiler could be used for, steam, could be used for heat, could be used for cooking. There's a number of different ways that that can be, utilized. That tends to be the simplest form that you're going to qualify, excuse me, for the minimum tax credits. Beyond that, going to cogeneration, electrical generation, or thermal generation, these areas really start to improve the ROI structure for these projects. We have projects out there, um, mid-sized projects, having a few kilowatt of power output is not uncommon. Medium to large or larger projects, we have megawatt generators out there that are really putting out a lot of energy. Those projects definitely pay for themselves very quickly. And if there's a way to tie into the grid from that, even better. There are, let's say, kickback isn't the right word, but there are multipliers for putting energy back into the grid and additional tax credits there that really boost the value of these projects. Otherwise, small and medium-sized projects, it's very simple to go to electrical generation and use it internally at the factory for the production process. Um, Depending on what your factory demand is, in some cases, we see offsets of 20, 30, 40%. It just depends on the relative nature of the waste or feedstock that we're using in the digester process. So here we've laid out a few things: primary sludge, secondary sludge, meat internals. The list goes on and on. I mean, there's so many different byproducts. Again, when you get into the biofuels, confectionaries, chocolates, bakeries, breweries, alcohol, refreshment manufacturing, the list just goes on and on. And the COD content is really all over the map. As I mentioned in the previous slide, we typically want to see BOD values greater than 2,000 milligram per liter. So roughly COD value, say 3,800, 4,000 or higher is a COD value. That's kind of the minimum uh, where we would apply a digester project. Just because we need to make sure that we have enough organic content there. But when you get to the point where you have existing waste products or waste sludges that can be combined with primary plant effluent or primary discharges, you can really start to improve the impact of the digester process. So we briefly discussed, why the feeds are important and a rough concept of how to apply the biomethane. Understanding the feed makeup is really the first step. That's the first thing that we look at. The second step is understanding how the reactor configurations differ, as each reactor has a different economic impact. So there are different operating conditions required to maximize the efficiency based on the type of feed that we have. So that's why we have so many different options for anaerobic digestion. We have your more conventional continuous stirred flow tanks. We have a recuperative thickening process where we have a digester in combination with essentially a glorified DAF unit that we use to boost the bacterial populations, boost the solids populations. And then we have granular technologies when you have systems that have more, let's say, soluble, basically just liquid, and it's like sugar water or starches, things of that nature. So they all differ in terms of retention time, operating temperatures, recirculation rates, and they all have a different impact on the bacterial efficiency and therefore the biogas generation. So here we've kind of taken, the core industries that we typically work with: dairy, distilleries, confectionaries, vegetables, fish, meat, etc., and divided into three separate categories in terms of three separate anaerobic processes that we typically use. And you can see how the incoming organic matter, in terms of the organic strength, plays a part in determining what type of digester that we're going to use. A well-designed system should be capable of well over 90% reduction efficiency in terms of reducing the COD and BOD values. In many cases, the reactor effluent or the digestate that comes out of the digester process can go directly to dewatering. So one big benefit there as we move forward in the presentation, keep in mind talking about ROIs. If you're able to take reactor effluent and go directly to dewatering, it's a huge, huge step in reducing hauling costs. So in most of these applications where just use poultry or agriculture as an example, where they have a lot of side streams, a lot of byproducts, a lot of sludges coming from DAFs and things like that. We typically see anywhere from 70, 80, and 90% reduction in the disposal costs. We can set up our digester to manage those types of waste, those type of byproducts and side streams. So significant reduction in hauling costs. Sometimes hauling costs or offsetting hauling costs more than pays for the cost of the digester, within a matter of 2 years in some cases. So uh, just keep that in your back pocket and when thinking about return on investment, ROIs, cost of digester versus offsetting, being able to reduce your disposal volumes. Historically, anaerobic systems were quite big and bulky. Most of the antiquated systems are like old anaerobic lagoons. You don't really see a lot of new anaerobic lagoons being built. They're just, can they work? Yes. Do they work? Yes, but it's not as efficient, very land intensive, and the biogas collection out of a lagoon process is completely different than these more high rate standalone tank options. Much more homogeneous biogas collection, biogas capture, more stable biogas production in these type of systems compared to the old school lagoons. Um, Hydraulic retention times typically can be a few weeks to only a few hours. Again, it depends on the type of digester process and the type of feed, byproduct, or primary effluent that we're trying to process here. So most projects that we are currently involved with, I will say the ROIs, factoring in tax credits, factoring in disposal costs, are probably on the 2 to 3 year window, and also factoring in the electrical cogeneration side of things. So these projects pay for themselves very, very quickly, um, and the tax incentives have a lot to do with that. So the optimal projects, just to recap, are typically those with significant hauling costs that can convert waste to electrical generation. These projects are going to have a very short return on investment. And in addition to that, and later in the presentation, we'll hit this in more detail, but there are methods for actual revenue generation from these facilities, whether it's electrical revenue generation or renewable natural gas generation. And there's some newer methods out there, which we'll talk about briefly at the end of the presentation, where we can basically do like an energy storage or even like a data banking, data mining option. Again, these are relatively new, but those are new ways to generate revenue on site for decentralized facilities. So briefly, before we get to the tax credits, part of what the Inflation Reduction Act, part of what the EPA, part of what Congress, part of what everyone is trying to do is boost the sustainability aspects of not only these projects, but just life in general. You turn on the news and there's always some crises with, you know, uh, famine or, water scarcity or even water pollution. So, what the United Nations has done is basically set up a list of sustainable development goals aimed at setting minimum metrics to ensure quality of life, environment, and geopolitical landscapes. Obviously, clean water and combating water scarcity is at the front and center of that. Europe has kind of been ahead of us here in the US in terms of how biogas has been applied and how it can help improve or promote energy independence for industry specifically. So they've been ahead of us for a while here. The beauty of all this is it's relatively simple to create a positive and circular impact for most industries. If you're an industry that produces a lot of waste, either wastewater or waste byproduct, liquid, solid slurries even, if it's high on organic, there is an inherent potential here to put this to work uh, while creating a more sustainable, long-term sustainable business practice, but also a better environmental impact. So if you walk through all the sustainable development goals that the UN has, just focusing on the water side, the wastewater side, the biogas side, we have the ability to directly impact at least 9 of those goals from these projects. So it's just overall, it's a good business message. So here we are at the Inflation Reduction Act. This is, we've talked about the basics of the waste to energy process and anaerobic options. So I imagine most of everyone on here on this presentation that's joined the meeting are most eager to learn about these tax credits and how it can impact your project or your operations or any future, planning. So the Inflation Reduction Act, what we're speaking about specifically is going to be within sections 45 and 48 of the Inflation Reduction Act. This was updated in August of 2022, so not quite 1 year ago. It was essentially updated to incorporate low carbon technologies and a larger focus on reducing carbon intensity. So qualifying biogas properties were rolled into this overall tax credit program. So what we mean by qualifying biogas property is essentially if you have a wastewater or waste product that we can apply anaerobic systems to and generate a biogas and methane, as long as that biogas and methane is repurposed and not flared, you will be available for specific tax credits. It can either be for sale or productive use. So productive use can be taking the methane back to your boilers, energy generation through CHP or generators, renewable natural gas, basically connecting to the pipeline and exporting the gas from the project. I will say when we talk about biogas and methane production, we typically, at least based on my experience, we typically want to see a minimum of about 100 to 150 CFM of methane production, 150 CFM to have the most uh, to have a starting point for favorable ROI, return on investment. So below that value, and it's not that it can't be done, it's just that the payback period on digesters can be a bit longer. So these tax credits are transferable, so kind of similar to how we do a personal taxes. If you move forward with a biogas project, you'll receive tax credits at the end of the project. Those tax credits can be applied directly to the project, or you can take those tax credits and apply it to your production facility. So we've had a few sites where the cost of the project was in the $20 to $25 million range, and they have 40% tax credit. That is a significant tax credit coming back to the project that can be applied in many different ways back to your production facility. So the basis of these ITCs are projects must begin before December of next year. So that's 2024. You'll have to show a minimum of 5% of the capital expense of the project is allocated or has been spent toward the purchase of equipment or engineering or something of that nature. Projects must be completed by 2028. So from today, we roughly have 5 years. Questionable whether that's going to be extended beyond that. I would like to believe that it will be, but we'll see. There are additional let's say bonuses or possible participation for renewable fuel programs, low carbon fuel standards, depending on where you are and what your end product is. But there are additional tax credits there for alternate fuels. So when we talk about going to, there is a way where you can convert or create hydrogen out of this process and using that as a hydrogen fuel, significant tax credits there. There's CO2 capture and sequester. Um, there's other models, the GREET model, similar to kind of the ins and outs of your overall carbon intensity scores, where you're looking at like cradle to cradle, gate to gate, what your transportation costs are, what your CO2 emitting is, what you're doing on the water, wastewater side. Um, all of this can impact your carbon intensity scores, which there are additional credits there as well. I believe that is on the next slide. I apologize, I'm getting ahead of myself. So the maximum investment tax credit for qualified biogas properties is 50%. So you can find this information in sections 45 and 48 of the Inflation Reduction Act. Basically, the program establishes a base minimum of 6%, but most projects qualify for prevailing wage. So there's a 5x multiple on that 6%. So that's how we arrive at this 30% eligible tax credit. I will say most projects that I have been involved with in North America, 30% is kind of the minimum. That's typically where most projects start. There are two potential bonus credits, one being an additional 10% for domestic content. Essentially, what you have to show is 40% of the manufactured goods for the biogas project are local costs. So 40% of your steel, 40% of your, pumps, equipment, erection, installation, a manufactured end product. If 40% of that is of domestic content, then there's an additional 10% bonus. So fairly easy to arrive at a total ITC of 40% in these cases. Additionally, there's another bonus for an energy community. This is broken down into a few different ways. If your site is on or near brownfield sites, so existing, power facilities, closed coal mining, coal fire operations, um, there's an additional bonus that is available. Or if the area has a certain percentage of direct employment or impact to the local tax revenue, or if it's based on, most of the economy is based on coal, oil, or natural gas. This is an additional way to have an additional bonus credit for these energy communities. So again, just to recap, 50% is the maximum. Most projects qualify for a minimum of 30. I think the highest I've seen on a personal project is about 45%, just to give you an understanding. So as Fluence, we can work with you on that. We have partners that can help kind of advise or counsel to work with your CPAs or your attorneys, what have you. We can put together kind of a base picture of what these projects might look like based on your specific setup, your specific production, and what your waste product and end goals are for the project. I briefly mentioned the hydrogen, CO2, and other ways of incentivizing the biogas. Um, it gets a bit more complicated when you're talking about emissions factors. The GREET model is probably most widely used to determine the ins and out of your emissions factors, but there is certainly a way to improve your carbon intensity scores. And if you can do that, there's additional credits in terms of electrical or heat generation from this process. There's also the potential to have significant tax kickbacks or tax credits, I should say, sorry, for sequestering CO2. These projects have kind of a minimum start point, like you need to have at least 1,000 CFM of biogas for this to really start to make sense. Um, so those, just to put it in perspective, those are very large projects. That would be tons and tons, tens and hundreds of tons of waste that would have to be generated to have that much biogas output. So this typically is more like for your regional cogen facilities where you have, tipping fees and people bringing waste product into a facility specifically for co-digestion. So now that we've gone over kind of the basics of the Inflation Reduction Act and the tax credits, we can turn our attention to more specific applications and see a few examples of how this can be applied. So, as I mentioned up front, many, many different industries out there. We try to typically lump these into uh, five main feed categories. Lipids, proteins, and carbohydrates are probably the top three in terms of how we break things down internally or process our designs internally, I will say. And you'll see that different industries actually have an overlap a lot, really, because a lot of these industries have a very wide product range internally. So dairy might be cheese, milk, yogurt, whey, you name it. Confectionaries can be anything from sugar, sweets to breads and bakeries. So a lot of overlap here. But we take these feedstocks, we apply it to the digester models that I showed earlier in the presentation, and we start to develop a picture of our biogas project and biogas output. So as far as the potential feeds that we can process, or we typically process, primary sludges. So if you have existing dissolved air flotation systems that generate excess sludge, if that sludge is not a current revenue source for you and it is a disposal cost, then this is arguably one of the best areas for digester projects and return on investment. Excess sludge from existing wastewater treatment facilities. So if you have an existing aerobic facility that has waste activated sludge, that is a consideration. Organic byproducts, so anything with meat, proteins, sugars, things like that. It could be liquid, it could be solid. Fermentation broths, fats, oils, greases, like dressing, salad dressing manufacturing or condiment manufacturing, anything with a high BOD or COD value. So we can look at treating these as a one-off, a standby, so you can have a smaller digester. Maybe it only handles your existing sludge from an existing wastewater facility. Very economical, very low footprint to do it that way. Or for new facilities that are looking for brand new complete wastewater treatment plants, you may use a digester to treat the entirety of your plant effluent. And then as we build out the digester process with a more complete wastewater package, then we look at, okay, what can we do internally to recirculate any sludge or biological byproduct generated from a wastewater plant so that we're digesting as much as we can and reducing the disposal cost as much as we can. That's going to have a very favorable return on investment there. So current drivers for waste to energy projects, projects that have existing surcharges. So if you're discharging liquid or solid waste right now that's going to municipality, a lot of times you can be fined based on your concentration or based on your liquid flow rate or based on the pounds of organics and solids that you're putting down the drain on a daily basis. This is a very favorable area, very favorable driver for waste to energy. You can turn that cost into an actual revenue or at a minimum, decrease your operating cost at your facility. Compliance is also obviously a big driver. You can't put anything down the drain unless you're going to meet minimum effluent discharge requirements, whether it be BOD, TSS, nitrogen, phosphorus in some cases. So this is something that we consider as well. Additional drivers for waste to energy, if your site is using natural gas for boilers or to run steam, etc., you can directly offset your natural gas usage from a waste to energy project or waste to energy process, I should say. Disposal and sludge management, I think we've kind of beaten that one to death here. Electrical and thermal energy, I think we've gone over that. Obviously, there's the sustainability of it all. A lot of industries are under the public eye these days to have the most sustainable business practice, but also sustainable operating practices. So these facilities, these waste to energy facilities, can certainly assist with that and boost those sustainability platforms and sustainability scores. And in certain situations, these waste to energy projects can be revenue generators. It just depends on the size of the project and what type of feedstock that we're working with here. So if we talk about the operating expense of these projects, of these waste to energy projects, typically with a digester, there is a positive net energy balance. Um, Again, we tend to think in terms of how much biogas and methane output we have. So we like to see projects that start with 150 cubic feet per minute of methane generated. That tends to be a nice starting point for these projects, all the way up to 1,000, 2,000, 3,000 for large projects. Typically, if you're thinking about an existing wastewater treatment process, if you're adding a digester process, there is a direct reduction in chemicals and a direct reduction in the disposal costs for sludge or byproducts. Big ROI there. I would say the average rate in the US in most areas for a tanker to come into a facility and move 6,000 gallons of liquid slurry or sludge or byproduct is probably $1,000 a truck. And we've been to sites where they have 40 trucks that come in and out on a weekly basis. That's $40,000 a week of disposal costs. So it is possible to take what you are currently disposing, put that in a digester, generate biogas out of that, get a tax credit, cut your hauling by 80%, maybe more in some cases, have biogas, have electrical generation. Uh, um, in these situations, the return on investment is very short. Um, Comparing to, more conventional aerobic technologies. So we still work in aerobic technologies. There's always a need for aerobic technologies, particularly when we're trying to get to, very low effluent levels. Sometimes you have to add a polishing step to get the BOD values down to, single digits in some cases. Um, so you're not necessarily getting completely away from aerobic technology, but there are systems out there where it's required and systems where it's not required. So it just depends. But if we're comparing an anaerobic process to a aerobic process that would be treating the same waste, the aerobic process, again, historically, carries a much higher cost, typically $5 or $6 per 1,000 gallons of wastewater treated in an aerobic process. That is just a general operating cost that people kind of live with. If you look at a digester technology for similar process, similar treatment, there is typically a net positive energy balance here. So you can actually reduce your operating costs, even have a operating cost back in your favor. So now that we've covered that, we're approaching the end of the presentation. I realize we're coming up on 1:45 Eastern time here, so I'll try to wrap this up in the next 5 minutes. But I wanted to leave you guys with an example of what a biogas project may look like for a specific industry. Here, I've chosen poultry just because we have a significant foothold in poultry and meat operations. So a typical biogas project.
Oh, you had it. It was all in the back seat. The envelope, the big pamphlets in the back seat.
Jason, it looks like you're muted.
Oh, thank you. How about now? All right, should be
Now
good.
I can hear you.
Thank you, thank you, thank you. Yeah, so typical biogas project for a poultry. I chose poultry just because we have a significant foothold in the poultry business, but it could be biofuel, distillation, brewery, confectionery, bakery, you name it. We have a large installation base out there. So um, this is poultry is interesting because of the relative strength of waste to the volume of waste that is generated. So a lot of different streams coming in from poultry. Poultry's process, kind of rule of thumb, 3 to 4 gallons per bird on a daily basis. So very a lot of water usage here. So you see poultries that typically have 1 to 2 million gallons a day of primary effluent discharge from the plant. So in these cases, sometimes it's not the most economical to put the anaerobic system for the full primary effluent. So what we would look at is, hey, let's look at the byproducts from this facility. 99.9% of the poultry processes out there are using dissolved air flotation. So let's look at a digester that might take the DAF sludges and byproducts from their operations and see what we can generate from this. So this is a very common approach for poultry and meat in general. It's also a common approach for many other industries that have a lot of side streams that can be, byproducts, whether it's spoiled product from your manufacturing, off spec product, spilled products, condensate lines, drip lines, things like that. All that factors in. So we would typically look at taking the sludge from the DAF process, very high in COD, high in solids, combining that with other byproducts, taking it to a digester, and creating a biogas generation process. From the digester, we would go directly to dewatering. So we would squeeze any remaining bacterial solids down to a minimum amount, maybe a few truckloads on a weekly basis for this facility. So very, very low total disposal at the end of the day compared to what they were initially doing. The part of the clarified portion of the DEF would go to kind of a normal aerobic wastewater treatment portion. Typically coming out of the DEF process, they may have COD values of maybe 800. So below that threshold that we mentioned for the organic strength that I mentioned earlier. So that's fine that we can take that to an aerobic system, more conventional process, much more cost effective to do it that way because the aerobic system is quite small and the equipment costs are typically a lot lower than the anaerobic cost. So again, thinking holistically, how do we put a full plant together where we can utilize this biogas, but we can get you to your discharge requirements as well. So this is what a typical process might look like. So if we kind of zoom in on the sludges coming out, so from the primary DAF unit, we have about 35 gallons a day, COD concentration of about 150,000 milligrams per liter, ppm. So very high COD value. So we're taking that COD value, this primary sludge, taking it to a digester, generating biogas flow rate of over 300,000 gallons a day. So that is significant here. That is enough for a 1 megawatt generator. So again, here we're talking about a facility that has a primary discharge of 1 million gallons a day. Of that primary discharge, we're taking about 3% of their taking about 3% of that to the digester process and able to generate 1 megawatt. So that is a significant energy output. This particular site paid for itself in about 3 years building the system this way. I won't get into much of the side stream treatment, but what you should understand is the digestate that comes out. in some cases is void of nutrient. In other cases, it will have nutrient. And when I say nutrient, I mean nitrogen and phosphorus. So sometimes we do have to add a polishing step to make sure that we can get that nitrogen and phosphorus down to a point where we can then discharge the final flow out of the facility. So if we take a look at how the system was operating before the digester upgrade and after the digester upgrade, by adding the digester to this process, that 1 megawatt generation generates about $1 million of energy production on an annual basis. So fairly significant for this facility and able to really decrease the return on investment for this particular project. So they went from having to pay millions of dollars a year in operating costs to actually having an income, because in this particular case, that 1 megawatt generator is going back to the grid. So to kind of wrap this up in a nice, neat nutshell, when we look at these projects and try to define the ROIs, the main factors, strength of your wastewater relative to your discharge permit. So the strength of the wastewater is going to drive the size of the digester, therefore the cost of the digester, and if these polishing steps are required. Surcharge values, obviously, some sites pay a few $1,000s a month, some sites pay a few $100,000 a month, different economical picture. But in either case, we evaluate what the surcharges are and how that impacts the overall return on investment. Hauling and disposal costs, obviously a big impact that we've kind of beaten to death today. Boiler usage, again, this is the simplest and easiest thing to do with these digesters. Take the gas back to an existing boiler. That's the easiest way to get tax credit. It's not necessarily a revenue generator, but it is a way to reduce the cost of the system because you're repurposing the biogas. Going to CHP, electrical or thermal usage can be a revenue generator. Some of the newer options on the market and that you'll see as the new RINs come into effect, the E-RINs, so electrical or electric tax credits that will be coming in the future. There are methods to put energy storage and either data banking data platforms on site. So not to digress too much, but basically picture this futuristic model where Google comes in and puts a Google data server adjacent to your site and uses some of the energy that you're generating from your facility, and they pay you to basically use energy for that data storage. So potential revenue generator there. We'll see how this plays out. RNG, we've covered that. And then project financing. Obviously, you have project financing capacity that directly impacts the ROI on your projects. Fluence does have financing and build, own, operate capacity. So depends on the, excuse me, depends on the size of the facility and what your specific objectives are, but this is something we can also approach. So to wrap things up in a nice, neat nutshell, just to give you an idea of a few kind of industry typical ROIs with the new ITCs, most projects that we're seeing today are going to have a 2 to 3 year return on investment. So these anaerobic projects tend to start probably around $1 million and can go upwards of $30 million. It just depends on what your specific production facility is and what your wastewater looks like. But in general, with the tax credits, the ROIs on these systems are very short, at least with the systems that Fluence designs and what we typically look at. So that, my friends, is the 30,000-foot overview. I know we're coming right up on 2 o'clock, but maybe we can get back to any questions. Let me go to the